Hi, everyone. Oh, thank you for joining us for this new episode of Additive Talks. Make yourself comfortable as we are going to discuss how additive manufacturing serves electrification and vice versa. Around this table is Danny, and we are still waiting for Dr. Amy Elliott, who should be here in a minute. So my name is Katie Sins. I'm managing editor and at 3D Media and your host during this conversation. So without further ado, I would like to give the floor to Danny so that he can introduce himself as well as the company he represents today. So Danny, good afternoon.
Good afternoon, Katie. Thank you for inviting me. I'm Danny. I'm the lead manufacturing engineer and additive manufacturing specialist at QDOT. I have a background in nuclear science and materials from the University of Birmingham. My previous roles were as an additive manufacturing research engineer at the Manufacturing Technology Center, and then as the additive manufacturing specialist at Arrival. At QDOT, we're developing some pretty exciting stuff. We are developing hybrid electric propulsion systems for eVTOL aircraft. So that is electric hydrogen hybrid propulsion. So zero emissions except for water, which is not too bad as far as an emission goes, but zero carbon for sure.
Okay.
The quite exciting thing about our technology is the thermal management aspect of it. So QDOT is a spin out of Oxford University, and we're currently based in the Harwell campus, spin out of the Thermofluids Institute specifically. But thermal management is a real pain for electric devices. So that's on batteries, motors, fuel cells, power electronics. All these things can severely decrease the performance of electric vehicles, and that includes cars, aircraft, and everything in between.
All right.
QDOT's innovative area of managing heat utilizes additive manufacturing to really boost that performance, get the most out of battery packs so that they perform better, they recharge quicker, they have a longer life, as well as managing all the other thermal aspects in order to really make hybrid electric powertrains for VTOL aircraft a genuine prospect, because it's quite difficult to make it viable without all these aspects as well. So we do that in combination with developing our own high density battery pack and hydrogen fuel cells to put all these things together into one beautiful machine that will be a QDOT drone. I believe we're going to be making a demonstrator that'll be available sometime next year. So that'll be a very exciting time.
All right. Thank you very much, Danny. It looks like Dr. Amy Elliott is already here, so she's figuring how to put on a camera. So hopefully, Dr. Amy, you'll be able to join us in a minute. I would just have a quick introduction with Danny about this topic. So, Danny, we used to see, the topic of electrification gaining momentum in the world of additive manufacturing, and most of the time, this trend focuses on the ability to solve climate change. Do you think that this trend is justified when we know that these mobility solutions are not widespread yet? When we know that, technologies like hydrogen, for instance, that could power these solutions are not widely accessible?
Yeah, I think they certainly will be one of the major aspects to improving the climate and trying to reverse climate change. When we take electric vehicles, for example, they all run on oil-based fuels, fossil fuels. A lot of power generation is from oil and gas as well. So moving away from these major carbonizing technologies into something that is emissions-free or zero carbon emissions will certainly be a massive aspect. And in terms of whether they're justified and making them accessible and widespread, additive is certainly something that can really enable that. It's a key enabling manufacturing technology. It can overcome some of the technical barriers to make them viable products in the first place. So I kind of mentioned with regards to eVTOL aircraft, hydrogen aircraft, these things are a burgeoning technology, and additive has a big part to play in that. Not just in the electronics components directly, but everything that surrounds that. So obviously spoken a fair bit about thermal management, and probably will hark on about that a bit more later on. But also R&D is a fantastic additive is in a fantastic place to assist R&D at this stage in terms of additively manufacturing parts of motors or even batteries. That's a viable thing at the minute. A big aspect of the cost of new electric vehicles is from that R&D. So making that affordable for a wider proportion of people is by reducing those R&D costs, and additive can play a big part in that. But also things like tooling. I mean, that's a pretty universal one when it comes to manufacturing in all sectors. But if we think specifically on electric vehicles, one of the major things to try and do to make them more viable is reducing their weight to give them more range or more power. So, for example, a shift away from metals to composites can be a big part of that. And that isn't just additive composites, but additively manufacturing the composite tooling or the composite patterns using things like large format additive manufacturing, which is another massively growing space of additive manufacturing. So that can be a really nice area to assist EVs or electrification. There's some companies out there, some startup companies like Saku, I think they're pronounced, and Blackstone, who are additively manufacturing batteries. And they can manufacture lithium-ion batteries or solid-state batteries to increase the power density of them, create custom shapes, and even claim to make them cheaper than traditional processes, as there's fewer steps involved in the manufacturing, as you can kind of do it all in one go, layer by layer. So combining those different elements together can really help improve performance of vehicles, make vehicles viable through electrification, reduce cost and reduce the barrier to entry for consumers and businesses to adopt electrification. And it really paints a positive picture for additive in this space going forward.
All right. Okay, great. Dr. Amy, can you hear us? Dr. Amy, hello. I was told that she was here. It looks like she's still in the studio, maybe. Okay, so Danny, let's continue. Before diving into these technical details that you just mentioned, I just wanted to know the different fields of activity where additive manufacturing can serve electrification, because you are working on a very specific field of activity at QDOT, and globally, I mean, generally, people use to sing AM and electrification being adopted together in electric vehicles. But I guess this is not the only field of activity.
No, it's certainly not. Electrification, I think, people have that tendency to match electrification with electric vehicles. Really, it's happening across all sorts of things. The obvious one is electric power generation and making that fossil fuel free, but even in traditional fossil fuel industries, additive manufacturing plays a lot there. So if we take, for example, fusion energy, which is the golden, the diamond, in fact, kind of energy source that a lot of countries around the world are collaborating to try and crack. Additive manufacturing is playing a role in that already. We at QDOT know that as we work with Tokamak Energy. We're engineering some critical systems for the nuclear fusion reactor, primarily around that thermal management aspect. Material science and thermal management of fusion is an incredibly difficult challenge because of the high energy particles flying around everywhere, degrading the materials and trying to convert that energy into something useful. So additive, with the new designs and materials that can come from that, is going to be an enabling technology for fusion energy.
All right. But the thing is that in electrification applications, now, if we go, into everything that is related to manufacturing, in electrification applications, electrical conductivity is key, but it's also a challenge. Could you please let us know why?
Yeah, so if we think about conductive materials like copper and silver, they are directly impacted by the quality of the print. So if we take laser powder bed fusion as a pretty common metal additive technology, the surface roughness and porosity of parts will negatively impact the conductivity of copper materials. Increased surface roughness is an increased surface resistivity. A lower density or higher porosity also means a lower conductivity. So there's going to be a lot of fine-tuning involved in trying to improve both of those things, or increase costs from post-processing, whether that's chemical smoothing or machining, or hipping, for example, to try and increase density. So there are some challenges there in comparing it to conventional manufacturing processes that can get you very dense, very smooth copper parts. But there are benefits to it as well in trying to get improved designs, improve winding designs for improved performance. And also a lot of these materials can be very expensive, or they can be quite rare, or come from strange sources like cobalt, for example, unethical sources. So utilizing additive manufacturing can help reduce the amount of materials that you use. You get higher material efficiency out of it. So there's some benefits there as well. And that kind of thing also can increase material security and supply lines. A lot of the materials in batteries, for example, are rare earth materials that primarily come from certain countries. So if for whatever reason those sources dry up, or there's some other international things going on, which means that your access to those materials is limited, then that obviously severely impacts your ability to make batteries and all these other products, which will be a hugely key part of everyday life within just a couple of decades.
Yes.
But more so.
Well, apart from electrical conductivity, what are the other specific items that you believe are critical, to take into consideration when thinking about electric conductivity and AM? Maybe you can just take your experience at QDOT as well.
Sure. So a specific experience with QDOT is a challenge in trying to find the right combination of machine and materials.
Yes.
Or I should say technology and materials, but same thing really. In trying to get the kind of fine detail resolution that you need with the kind of throughput and cost that you need with the material that you need.
Yeah.
So, for example, we are working on metal binder jetting.
Yes.
That has the kind of feature resolution and throughput that we need for a viable product and for the kind of performances that we require. But it's some serious challenges with certain materials, with certain part sizes. It's harder to scale up the part for various reasons with regards to the sintering stage, metal binder jetting. If the part's too big, or the walls are too thick, or it's too inhomogeneous, then you'll get warpage, cracking, and all sorts. So we're working with a few very intelligent people, and we have some patented innovations in this area of sintering for metal binder jetting in order to overcome some of these challenges to really create a world-leading product when it comes to thermal management. So that's quite exciting. But there are some other things there as well, and that's relating to sintering, but also laser powder bed fusion. Mentioned with regards to things like roughness and porosity, but also there's the way that the grain structure is comes together as you build these parts or sinter these parts, and effectively the thermal management throughout that part that can negatively or positively impact the properties of that material. So there's a lot of R&D involved in trying to control the microstructure growth of your parts effectively to get the most out of them.
All right. And if we want to assess, the manufacturing readiness level of a given technology, you mentioned that you're using binder jetting for your electrification applications. How do we assess, the manufacturing readiness level of binder jetting? How do you proceed at QDOT, for instance?
It feels like quite a hard one to assess on a technology-wide level, because very recently metal binder jetting has split off into several different routes. You have some very small, very fine feature resolution, Like,
first, I have to say that I'm quite surprised that you're using binder jetting. I'm used to hearing people say, okay, powder bed fusion is often the technology of choice for such type of application. So first, why binder jetting?
really, it's because of the feature sizes that we can achieve. So we can achieve feature sizes in all build directions of less than 100 microns.
Mm-hmm.
And it's that kind of feature size combined with the requirements of thermal management, surface area, things like that, that means that that's a technology that we can go for. In order to achieve that kind of resolution with laser powder bed, it requires a lot of fine tuning, some very high-end machines, and it's quite a pain. And doing that in all directions as well, rather than just, for example, straight walls going up, can be very difficult. So that's why we like metal binder jetting. And yeah, it's one that not many people work on, so that's also quite exciting.
Okay. All right.
Yeah, assessing the technology readiness level of say metal binder jetting, that in particular is split off in a few different directions. We have the likes of Digital Metal, now Mark Forge, I think, tend to do quite fine features in small build areas. GE have come into the space with larger parts, casting replacement, so its resolution's a bit lower, but better for larger parts, thicker walls. And then I guess you've got the likes of HP in the middle. So can't really assess it as a whole because they're all doing their own thing.
Yeah.
It all seems to be a bit kind of working with industry, so it's all quite quiet as to what level each one is at, rather than just selling products on the market and letting everyone go crazy. But our TRO level, I think it's in that middle zone, that valley of death, taking it outside the academic space, and we're now in the stage of industrializing it, making it work with some new and advanced materials.
Yes.
And trying to take advantage of it in those other ways that I described earlier, in terms of controlling the microstructure, getting the most out of the feature sizes. And then hopefully soon we'll be in that 789 TRL.
All right. Just a quick reminder for the audience, please feel free to send your questions in the Q&A chat. Oh, I can see there is already one there's already ones that pop up. So I just published it. So I was about to say, okay, feel free to send your questions in the Q&A chat. Yeah, so we are going to pause at some point. Just after the next question I will ask right now, and Danny will be able to answer them. So yes. So Danny, before we respond to the questions of Victoria, I wanted to ask, is it fair to say that additive manufacturing only makes sense if there's a new and complex design? Are there any, could you please just tell us about some of the design challenges that you've often faced in some applications and the way you address them? And then after that, we will be able to respond to Victoria.
Sure. So additive is quite well known for having a lot of design freedom, but that doesn't mean that it's free of freedom.
Yeah.
I mentioned that a potential limiting factor for things like copper and silver, which have excellent conductivity and are used pretty widely in electrification. Surface area can be a problem. And in laser powder bed, for example, support features internally, externally will reduce the surface roughness of these parts. It means they require more post-processing. So designing parts that require the fewest amount of supports possible is something that is pretty critical to laser powder bed. In binder jetting, supports aren't needed in the printing step. The printing step is an absolute breeze, but the sintering, the depowdering and sintering steps are more of a pain. So trying to get the powder out of these complex parts, which are very delicate in the green state, can be a challenge. And sintering these parts can be an even bigger pain as well. There tends to be warpage, cracking, delamination. So we have to design the parts in such a way so that the powder can easily be removed, but that doesn't affect the quality of the part down the line. And you still have to design for overhangs. Sometimes your supports have to be designed into the part, potentially for removal later through things like machining, but also adding or reducing the stress concentration in the part. So reducing sharp corners, sharp edges, things like that. Size of a component is also a key part when it comes to binder jetting specifically. We've patented a method such that we can combine parts together to create a single part after sinter. So that way we can overcome some of the challenges of metal binder jetting.
Yeah. But can it, I mean, when you say size is also a key part, can it cause some challenges at the design level? No, not really, right?
Well, to some degree, yeah. You want to be able to design the part so it naturally fits the build process in mind. With laser powder bed as well, you suffer a significant amount of thermal stresses during building. And bigger parts naturally present a bigger problem there. So I guess there's a design consideration to be made as to whether the part is printed as one whole, or is it made as an assembly? Does it still work if you assemble it together afterwards? Do you choose welding, bolting, whatever it may be?
Okay. All right. Let's take Victoria's question, if you don't mind. So Victoria is asking, are there applications for polymer additive manufacturing given the introduction of metal replacements such as PEEK and Ultem? And I like these questions.
Yeah, I think polymer often gets overlooked when it comes to electrification. Naturally, because it generally has pretty poor conductivity. But there are a lot of applications widely within the electrification sector and obviously across aerospace and automotive. But thinking specifically in this idea of conductivity electrification, these kind of parts can be metal plated with copper, for example. And with that, you can create a part that is lightweight and conductive. And also, in the case of PEEK and Ultem, can also be fire retardant. So that is one thing that I think often gets overlooked as a potential route for electric components, which I quite like. Generally, using, as I say, using polymer and composite parts across wider applications in order to reduce weight of vehicles and things is also another great aspect.
Okay. Here's another one from Eliseo this time. The combination of copper and SLM is often mentioned as the ideal mix of solutions for electrification applications, electric motors in particular. Are there any other technologies and materials you've explored in your application?
Yeah, so copper and laser powder bed fusion is that very common one. Not one that I've explored, but silver is another very good one. It actually has a higher conductivity than copper.
Which one?
Silver.
Okay, silver, yeah.
Yeah, and it's not super commonly used compared to copper in traditional industries, but it's because it's quite expensive. So there's potential options for cost reduction and reducing the amount of material used by using silver. Also, there's been research recently on combining copper and silver as multi-material, not as an alloy, but actual multi-material steps in the print. So targeted or selective use of silver within a copper composite, if you like, can also be another route. Aluminium is another very good one. Higher mechanical performances than copper, but still has great conductivity. So certain applications may be load-bearing, but may require that thermal or electrical conductivity. So aluminium is a good one. And I've also obviously mentioned metal binder jetting a fair bit as well. Gets a little bit overlooked. But also like bound metal deposition, like metal FDM. You see quite a bit of copper usage growing there. And I think that's because it's quite an energy efficient printing process. Printing copper in laser powder bed is quite energy inefficient because copper reflects light very well. So you have to either print much slower to increase energy absorption or have a higher energy laser. But when over half of your energy is being reflected, that's quite low energy efficiency. Whereas if you can print it as part of an FDM part, it's more accessible. You use very little material. You don't have to rely on or work with highly oxidizing, dangerous metal powders. So that's another good one that has a much lower barrier to entry in terms of cost and skills for working with small and fairly simple copper components.
Danny, excuse me, I'm hearing some sound in the background. I'm just wondering if it is Dr. Amy's sound that we are hearing. I don't know if you hear that sound. Okay.
I think it's coming from yourself.
Oh, for myself. Oh, sorry. Okay. Please go ahead. I will just mute it.
I think I was pretty much finished with that question anyway.
Okay, we have a new question coming from Dr. Christian Friedrich. Do you have specific part where you use AM in electric drives?
So like electric motors, that kind of thing.
Maybe Dr. Christian, can you specify your questions?
If you do mean like electric motors, then yeah, we don't have that specifically, but it is a growing area in terms of additively manufacturing like copper coils and things that result in better performance than conventional parts. So these things can be used in like esports and high performance vehicles. And generally, esports and high performance vehicles are obviously not a wide market accessible climate change beating beast, is actually a very important aspect of technological development, because you really push boundaries in your technology, and that drips down into your consumer vehicles. So F1 is a great example where things like composites and additive manufacturing are used an awful lot, and that bleeds into those car manufacturers' consumer vehicles. So yeah.
Yeah. Yes, let's move to the next question. This one is from Bram. Speaking of multi-materials, be careful. Be careful on the way you answer these questions. Bram is very smart. Speaking of multi-materials and conductivity, often a combination of conductors and isolators are needed in electric and or electronic parts, separation of loops in cores. How do you approach that in additive? Very good question. Thought you.
Yeah, that is a good question. I suppose the sector for multi-material printing is minute compared to single material printing. Generally, they are done as separate processes, or in the case of things like copper coils, they'll be then coated in an insulating material that is a non-additive aspect. So it doesn't, just because it can be done doesn't mean it has to be. But for example, Saku's printing process, without knowing too much of the details, they print metal, polymer, ceramic, glass all in one go per layer. So they've found a way to print all these components together, all these materials together layer by layer to create their complex 3D printed batteries. So, but that's a bit more of a secret and industry leading example, not an everyday electrification example.
It's something you can tell us all. So, okay. All right. I just wanted to take just a couple of minutes to apologize again on behalf of Dr. Amy. She's actually here, but for some reason she can join us, and I don't really know why. And I believe it should be a little bit frustrating for her, for not joining us right now. Yeah, because she's trying to speak, but for some reason we can't hear her, and I don't know. My colleague behind the back is trying to speak with her and trying to solve the challenges that she's facing. So yeah, moving forward, Danny, just to continue our conversation, moving forward, do you think additive manufacturing could meet mass production requirements here?
Short answer, yes. The couple companies that are working on additively manufactured batteries claim that they'll be able to make them cheaper at high volume than conventional processes. So that would be a major success. There's a few technologies coming out these days that really do push the idea of the volumes that additive is good for. So metal binder jetting is a very high throughput process on the metal side of things. New technologies like STEP from Evolve Additive really push the boundaries in terms of polymer parts. And there's also similar examples in ceramic and other examples in metals and polymers as well. So really that's a technology-driven one, I think, rather than application. But I think there's so much desire for high throughput additive manufacturing that it will reach there one day. And one of the main barriers to overcome for additive in general applications is its cost, and its cost will come down through wider adoption and producing at scale.
Yes, I believe so. Do you, I mean, apart from binder jetting, what other technologies, and this is, I mean, I believe this is not necessarily additive, but what other technology do you use, with AM to achieve, the best results?
Sure. So I think sometimes people get hung up on additive being the be-all end-all one day, but really it sits alongside other conventional processes like machining, casting, injection molding. It complements them. It hopefully will give them a run for their money, but I think it will sit alongside them rather than entirely replace them.
Yeah.
But other complementary technologies really sit around the post-processing of additive. So I mentioned briefly on polymers, things like metal plating, that can be conductivity and lightweight conductive parts, but also for things like RFI, MRI shielding, which is quite important in things like self-driving vehicles and aerospace components. And then general post-processing, so machining, chemical smoothing, hipping for densification. And while not a technology and a little bit boring, but very, very important, is standards as well.
Yeah.
Industry standards, we're seeing the implementation of standards in aerospace being very beneficial for the aerospace sector, increasing the adoption there. So,
thanks, Danny. Dr. Amy, can you hear us? Can you?
Hi, yes, I finally made it in. So sorry. It was like being in one of those breakout rooms, right? Like all by myself. I was trying everything I could think of, but now I'm on my phone. So
I'm so sorry
for being late.
Yes, so sorry for this inconvenience that you've experienced for this session. We've never had a speaker, facing such, such constraints to join the platform. But anyway,
what can I say? I'm just special, I guess. So.
But that's okay. You're here, and that's the most important. Have you been able to listen a little bit to the first part of the conversation with Danny?
I have not, so I don't know if you want to ask different questions, because I might just repeat exactly what he said. Maybe, I don't know.
Not sure, but I had specific questions regarding electrical conductivity. Danny responds to these questions as well. We also had some questions for mass production, but just for the audience to have a different response to that electrical conductivity challenge, because it's both a key item in electrification applications. Could you please just explain the reason why electrical conductivity is so challenging for this type of application? And if this consideration limits the type of AM processes and materials one can leverage for a specific application. Danny mentioned that they use binder jetting. So if there are any other technologies that may be used for this type of application, this could be interesting to speak about.
Yeah, no, I'm a huge binder jet fan. That's my main area of research. So they've done some great things with copper and binder jet. So what I know about electrical conductivity is, like copper is like the material, right? Like everybody wants copper. It's just got such great electrical properties. But then if you add anything to that alloy, like it just starts to drop that conductivity. And so we know that we can process copper with laser powder bed fusion, but only an alloy of copper actually. So NASA's developed this copper alloy that works with laser powder bed fusion, but it's got, I think it's like 80% electrical conductivity. So they actually designed it for thermal. So they're designing it for rocket nozzle parts. And so that's the challenge, is how do you get a 3D printed copper part that doesn't have extra things in it, extra alloying elements. So binder jet would be a good example of that. If we can reduce the amount of carbon we leave behind, then that's great. And then another thing is microstructure. So annealed copper is, has the best conductivity. That's the benchmark. Single crystal copper, I think, would probably be the best. Again, I'm not a material scientist, but the closer we can get to that and is the better. And so for binder jet, if you can do an anneal, well, with any metal additive process, you can do that anneal to help as well. But it is something to think about when we start picking how we want to make these copper things is, can we actually process pure copper or get as close to pure copper as possible?
Okay, great. There's also one question that I found very interesting to discuss again, the combination of copper and SLM. You mentioned copper, and it just came back to me right now. The combination of copper and SLM is often mentioned as the ideal mix of solutions for electrification applications. And we were wondering if there are any other technologies and materials that you've explored in your various applications. Danny mentioned silver. This question is actually one from the audience that I'm just repeating to see if there are any different responses that can be suitable for this type of question. So yeah,
so I think the thing with silver is just cost, if I'm not mistaken. So we can make, I would venture to say we can make pretty close to the alloy that we need and the shapes that we need with whatever process we decide to put money into, right? Like, I think the solutions are there. I just don't know in terms of like silver, if the price point would be there. And then also, it's interesting that laser has been identified as a solution for electrification, because laser is like really, really expensive actually. So, it makes sense for aerospace and medical for sure. But, we know it doesn't make sense for automotive right now. That's just not the price point that it's at. And so I don't know where electrification falls into that. I would think it would fall more on the automotive side of the cost spectrum. So that's interesting that laser has been pointed out as one of the solutions, because I don't know, like when you look at the cost, it doesn't make sense to me, but I don't know everything.
But I think Danny mentioned it as one of the most important challenges right now in this specific field of activity, right, Danny?
Yeah, I think I was saying that it's where most of the R&D is going, it feels like. And yeah, Amy mentioned lots of copper alloys and things like that, trying to make them work for conductivity. I think I also mentioned that copper is very reflective. So laser powder bed is not a very energy efficient process for making electrification components compared to things like bound metal deposition and binder jetting, where you can more energy efficiently create parts, and bound metal deposition more easily and cheaply make them.
Yeah. There is one question, Danny, for you, I think, in the Q&A chat. What are some of the manufacturing challenges the team at QDOT faces to develop powertrains for electric and hydrogen VTOL aircraft?
I think one of the major problems in manufacturing that we're having is costing for prototype. So not necessarily just additive prototypes, but general prototypes of different areas of the aircraft, and which routes to go down at this stage compared to a production. For example, do we go for a cheaper, more cost-effective like aluminium solution at this stage and move to composite for our production stage, trying to source cost-effective solutions for that for a small startup like ourselves. So that's a major problem. Another one is the talent pool for a bunch of these areas. The talent pool for hydrogen fuel cells is very small. It's a relatively new space. So trying to get the right kind of talent that can really help with that is a challenge, but we've got some great people working on it. So.
Okay. All right. Do you have any questions for Dr. Amy since we are here?
Not at this moment, but if I come up with any, then I'll let you know.
Okay, I still have one for you, Dr. Amy. I wanted to know how the team at ONL actually explore AM and electrification. If you can just give us a quick context on how you work with the technology and how you advance this specific field of activity, because I know the team is working on several types of projects, but if you just have, if you can just share a little bit with us, that could be great.
Yeah, so we do a lot with electrification in general. Obviously, we're a Department of Energy lab. And so we explore new electric motor designs and then, branching out that optimization towards our manufacturing rules and additives. So previously, you think about these coiled copper stator components. But now we can think about these printed copper coil. You call them coils, but they're not coils anymore. They're printed copper pieces. And so that's the kind of thing that we're looking into, as well as, what can we additively manufacture for wireless charging? What are the power transfer components, the step down, that the transformers components that you could additively manufacture. And so we kind of look around the whole problem and see, where's the low hanging fruit? What can we additively manufacture and optimize for, electrical conductivity, field generation, that kind of thing. So really kind of all over the place. But then also in terms of, I think hydrogen was brought up too, there's a lot of, that's a ripe area for evolution, because there's not so much infrastructure already built. So what can we do to think ahead and insert additive into the performance requirements, right?
Yeah. Oh, hello? Do we lose her again?
I can hear you. Can you
okay,
me?
All right, great.
A little bit stuttery.
Yes. Okay, that's fine. We have one comment from Bram. The first real copper parts in LPBF are slowly starting to come out. This is driven by laser development, green light, ring-shaped spot, but also via material science. I've myself seen two interesting ones so far in LPBF that went well above 95% IACS. So that was Bram's comment regarding those copper SLM, the combination copper and SLM. So that's it. I particularly never shared this part, and I've never heard about it. So I would be glad if Bram, you can share us, quick links for us to share with the public, if it's possible. So yeah, that's it. There was one question that could be interesting to discuss from Victoria May, Dr. Amy. Are there applications for polymer additive manufacturing in this specific field of activity, given the introduction of metal replacement such as PIC and Alton?
Yeah, so polymer is a tricky one because it comes down to that cost thing. I don't know if you've ever tried to price a plastic part and online somewhere by Service Bureau, but they're pretty expensive when it comes to injection molding. And so, I think in terms of plastic for electrification, I think we'd be looking at, maybe enclosures or structural components. But that one I scratch my head on. I'm not sure.
But moving forward, apart from binder jetting and, for instance, SLM, what other type of AM technologies do you see as a great production candidate for this field of activity?
So just full disclosure, I'm biased. I do work in binder jet. I've done multiple cost models of binder jet versus, other technologies. And it really is the fastest and cheapest. It does have an Achilles heel in that sintering component. So if you're not familiar, for the audience, binder jetting is inkjet printing powder in a shape that you get. So you get this green part, like a piece of pottery, and then you have to go fire it. And so when you're firing it in a process we call sintering, there's distortion. And so there's still a lot to work out with the distortion side. So binder jetting isn't like the clear cut yet, but I think there's a lot of opportunity there just because that price point. Like some of our models show that, you know, binder jet's a 20th of laser. So in terms of cost.
Yeah. All right. Moving forward, what should be, according to you, the key areas of interest or areas for improvement in that, you know, industrials should look up, you know, to explore AM for electrification applications?
So I think modeling is a great place to look. So we have tools to build optimized motors, electric components, batteries, but do they take into consideration the design rules of additive and the design freedoms? I think multi-materials would be great to look into as well. We can make, you know, functional systems, you know, functional artifacts instead of just, you know, single alloy components. So yeah, I think those are two areas to look into as well.
Okay, great. Dr. Amy, before Danny replies to these questions, do you have any questions for him? Because maybe you do not know each other. So Danny is working for QDOT. So Danny, do you want to just explain to Dr. Amy what you guys are doing exactly at QDOT, just in case she has any questions for you before we move forward to the last question?
Yeah, sure. So at QDOT, we're developing hybrid electric hydrogen powertrains for eVTOL aircraft. We're starting off with drones because it's a much nicer technology demonstrator testbed for us. And we're utilizing additive manufacturing really in the thermal management aspect of all that to really get the most out of it, to make it a viable product, because hydrogen is quite difficult to fly. And batteries can perform better when they're much better thermally managed. Their life is longer, so they need less charging time. They need replacing less often. All the combination of those good things really create a fantastic powertrain for sustainable zero carbon emission aircraft.
Thanks, Danny. So yeah, I was asking if Dr. Amy, if you have any questions for Danny.
No, that sounds great. No, I don't have any questions. That sounds super exciting. I'm a big hydrogen fan. And the additive for thermal is always a win. We can build, you know this, but you can build the best heat exchangers with additive that, you know, you can never dream of with conventional manufacturing. So I think that's a really exciting mission that you guys have. And I do apologize, I have to run. I had to.
No problem. This is
yeah.
This is actually the end of our panel. So
gotcha.
Last question will be just to ask Danny if he has something else to conclude. If he want to, you know, highlight some of the key areas of interest that he sees, you know, for industrials to explore.
Yeah, sure. I think another one is on much larger components as well. So for components, things like for nuclear and for fusion, and also oil and gas, I suppose, is, for example, large-scale DED and wire and other forms of DED to make these normally really difficult, very expensive components that can take over a year to make, that can be reduced to months or from months to weeks. So everyone focuses on the minute on smaller conductive kind of components, but another factor is enabling it, those technologies and power sources in other ways that may seem less direct. So I think that's a good one.
Thank you very much, Danny. Thank you very much, Danny and Amy, for joining us for this conversation. Really sorry again for all these constraints that you actually face for joining the platform, Dr. Amy. Thank you to the audience for listening to us until the end. And thanks to Bram for sending a couple of links regarding the key applications in this area. If you didn't save these links, or if you didn't save the link, please reach out to us or reach out to me. I'll be able to share it with you personally, inbox. On this good notes, I would like to wish you a very great end of day, and stay tuned for the next panel that will be announced. So stay tuned and stay safe wherever you are in the world. Thank you very much. We'll now close the platform. Thanks.
Thank
Have
you.
a nice day.
Cheerio.